Yuppers. All right, so this right here is the chapter 2 review problems that I set up for you. I'm going to do the displacement and velocity section with you. What we've got for this first one right here is a graph of position versus time. And it says on the graph in figure 2-19, what's the total distance traveled during the recorded time interval? What is the displacement? So the distance traveled, in this case, is going to actually end up being the same as the displacement, because if you calculate your displacement, you ended at 6, all right? You started at 1, 6 minus 1 gives you 5. And in this particular case, because you didn't go backwards, all right, your distance is also 5. You went from 1 to 6, all right? If we cut back, we would end up with a displacement that's different than our distance. But anyway, the answer to number 1, the total distance traveled during the recorded time interval and the displacement, they are both 5. All right, let's move on. 2, it says, on a position time graph such as figure 2-19, what represents the instantaneous velocity? So the velocity at one moment in time is represented by what? And the answer is the slope. Okay? If you look at how this thing's pointing, you can think of it, think like you're riding in a roller coaster car on top of this. At this moment right here, the roller coaster car would be facing like that. And as it goes here, it'd be facing like that. And as it goes here, it'd be facing like that. And then it would come down. All right? The line made by that roller coaster car is your instantaneous velocity. So our velocity here is pretty much 0. And then our velocity gets greater and greater and greater. It's increasing, increasing, increasing. And it's decreasing, decreasing, decreasing. And then it's back to 0. Okay? All right. That was number 2. Number 3. Sketch a position time graph for each of the following situations. An object at rest, an object with constant positive velocity, an object with constant negative velocity. Here we go. A, for an object at rest, here's time, here's position, and it would just stay the same the whole time. It's at rest. Doesn't matter if you drew your line down here, doesn't matter if you drew your line up there, as long as your line is flat, has a 0 slope. It's at rest. B, an object with constant positive velocity would look like this. Time, position, there we go. Straight line going up. Doesn't matter if your line starts here, if your y-intercept is bumped up a bit. Either way, it's a straight line going up. Positive velocity, see the slope is positive. And then lastly, for C, constant negative velocity, here we go. Time, position, it looked like this. There you go. Okay? Doesn't matter, once again, where you start this. We just want to see if the slope is negative. Okay? So that is number 3. Number 4. The position time graph for a bug crawling along a line is shown in figure 2-20. Determine whether the velocity is positive, negative, or 0 at each of the times marked on the graph. Let me do that. First, let me find figure 220. All right. So here's figure 220. For time 1. And which one am I doing? I'm doing problem number 4 right now. All right. For time 1, my slope is negative. So my velocity is negative. For time 2, my slope was negative, then it was 0, and now it's getting positive. So my velocity is positive. For time 3, it's positive, positive, positive. Oh, still positive at time 3. For time 4, let's see, looks to me like it's negative, just barely negative at time 4. And here's the deal, time 4 is kind of hard to see. Like you could say, but told, what if time 4 is right there at the top? Right at the top here, its velocity would be 0. So if I gave this to you on a test, and it was this ambiguous, I would accept 0 or negative. Anyway, at time 5, it's definitely 0. That line is flat. So at time 5, your velocity is 0. What would the units of your velocity be? Units of your velocity would be meters per second. Okay, so that's numero 4. There's 5. 4, there's 5. Okay, this one says, use the position time graph in figure 220 to answer the following questions. During which time intervals does the velocity decrease? During which time intervals does the velocity increase? So we're talking about velocity decreasing and velocity increasing, which is technically acceleration. All right? So we want to see, they're not just asking you where's the velocity negative, where's the velocity positive. That was the last problem. They're asking you how is the velocity changing? I'm going to describe it to you, and then you can fill in the time intervals on your own if you want. It gets a little iffy because some of these transitions occur in between the time intervals. All right? So right here, your velocity is negative, and it's staying negative, and then it curves, and your velocity becomes 0. So if you go from negative to 0, your velocity is increasing. Then here, you go from 0 to positive. So for that interval, your velocity is increasing. And then you go from positive back to 0. So there your velocity is decreasing. Then you go from 0 to negative. So your velocity is decreasing. And then you go from negative to 0. So your velocity is increasing. It can be hard to keep straight in the head. Like I said, think of the roller coaster. Put your hand on it, use a ruler, use something like that. Which way is it pointing as it rides this curve? All right? All right. Oh, look, the announcements are in for tomorrow. Okay, number 6. Number 6. If the average velocity of a duck is 0 in a given time interval, what can you say about the displacement of the duck for that time interval? So if a duck's velocity is 0, over that time interval, its displacement is going to be 0. All right? You can think of it, if you want an equation to help you, average velocity is displacement over time. Right? If this is 0, then 0 times t is going to be 0, and delta x is going to be 0. Or you can just think it through logically. If the thing is not moving, has no velocity, then its displacement is going to be 0. 7, velocity can be either positive or negative depending on the direction of the displacement. Time interval delta t is always positive. Why? The reason is time only goes in one direction. It only goes forward. I can't start this video at 0 minutes and end it at negative 15, right? The time progresses forward. That's the way we view the world. Okay? Number 8. A bus travels from El Paso, Texas to Chihuahua, Mexico, I like saying that, in 5.2 hours with an average velocity of 73 kilometers per hour to the south. What is the bus's displacement? Pretty simple problem. Here's your equation. Average velocity is displacement over time. The reason we can use this very simple equation right now, there's no acceleration we've got to deal with. All right? When there's no acceleration, you're dealing with your average velocities, you can use this equation. So, average velocity is 783 kilometers per hour, and my time is 5.2 hours. And my question is, what's the bus's displacement? My question to you is, do I have to convert anything? The answer is no, I don't. Got hours, my time is in hours. I got kilometers on top, so that means my answer will be in kilometers. Let's work it out. 73 equals delta x over 5.2. Delta x is, I need a calculator. Here's my calculators. 73 times 5.2. Bingo, bango. 379.6. 379.6. 379.6 what? 379.6 kilometers. That's how far you went. Okay? All right, and this was number 8. Let's see, number 9. Same kind of problem. Erase this one. Number 9. A school bus takes 0.53 hours to reach the school from your house. Time, 0.53 hours. The average velocity of the bus is 19 kilometers per hour. So my average velocity is 19 kilometers per hour. To the east. Okay, they give you that because it is a velocity, so you definitely have to have a direction associated with it. What is the displacement? So they want to know, what's the delta x? Same equation. Average velocity is delta x over t. 19 equals delta x over 0.53. Delta x is 19 times 0.53. 10.07 meters. Yeah, 10.07 meters. Oh, hold on. Meters. Losing my mind here. 10.07 kilometers. My time was in hours. This is in kilometers per hour. My answer is going to be in kilometers. Whew, close one. One of these we're going to have to do some unit conversions for, so you'll get to see that. So that's number 9. Number 10. Here's a squirrel running along a clothesline in number 10. And they ask, move that up a little bit. Okay. And they say, what's the squirrel's displacement at time 3? Let's look at this graph a little bit first. So in 1 second, the squirrel runs up to 4 meters. And then the squirrel runs back to where it started. Somebody was confused by this in my other class. They said, how can it run this way? And so that's easy. It just means it ran backwards. So the squirrel runs back to where it started. And then the squirrel runs down to -2. And then it hangs out at -2 and does nothing. And then it runs back to 0. Okay? So what's the squirrel's displacement at the time 3 seconds? So at 3 seconds, where's our squirrel? Our squirrel's at -2. Well, where did he start? He started at 0. So the difference between where he ended and where he started is -2 meters. So the answer to this question is -2 meters. What's the squirrel's average velocity during the time interval between 0 and 3 seconds? So, that squirrel ran, remember, average velocity is displacement over time. That squirrel ran -2 meters in 3 seconds. So his average velocity would be 0.7 meters per second. You can put 0.6666. You can put -2/3 meters per second. The important thing is that you have meters per second. All right, how do I know it's meters per second? This is in meters, and this is in seconds. All right, so there's your squirrel problem number 10. Let's move on to number 11. And fear not if you think this is easy. They will get tricky. Number 11. Oh, here's your time conversion one. The Olympic record for the marathon is 2 hours, 9 minutes, and 21 seconds. The average speed of a runner achieving this record is 5.436 meters per second. What is the marathon distance? All right. If you're wondering why I'm dressed like this, I want it to be an appropriate workout attire for this marathon running problem so that you guys will get excited about it. Either that or I've just got time to kill after I came out of the weight room and I didn't feel like getting changed twice, especially because I smell bad. Either way, you make up your own story. So, here we go. Let's figure out what the time is. This is number 11. Our time is 2 hours, 9 minutes, and 21 seconds. What do we want to convert that to? Well, if they give us this average speed, in meters per second, 36 meters per second, then I want my time in seconds. So I'm going to do 2 hours times, I know that there's 60 minutes in an hour, so this will tell me how many minutes there are. There's 120 minutes. times, I know there's 60 seconds in a minute, and that gives me 7,200 seconds. So that's the hours part. Now the 9 minutes part. There's 60 seconds, 9 minutes. So that's 450 seconds. All right. Yeah, looks good. All right, and then lastly, I've also got 21 seconds. I add all those together. 1, 7, 6, and I get this many seconds. So my time is 7,671 seconds. It's a lot of seconds. You ever want to count to 2 hours? Count to this number. Well, 2 hours, 9 minutes, and 21 seconds. Then they want to know what's a marathon's distance. So they're looking for the displacement. They're looking for the delta x. All right. What you do is you plug into the same equation we've been using. Average velocity, delta x over t. 5.436. This is a really good time for a marathon, by the way. Well, I guess they did say the Olympic record. 671. Anyway, doing the math, I get that this person, 36 times 1, woo! This is 41699.6 meters. It's a lot of meters, okay? The marathon's like 25 miles. So here's your answer. Very far. Okay? The answer to the question, what's the marathon distance? Too far. All right, that's number 11. Let's do number 12. Scroll up to it. Oh yeah, this problem. Okay, so number 12 says, 2 cars are traveling on a desert road, as shown in figure 2-22. After 5 seconds, they're side by side at the next telephone pole. The distance between the poles is 70 meters. Identify the following quantities. I want to scroll this up a little bit more. All right. So here's car A in blue, and here's car B. And this is 6:31 and 0 seconds. The next telephone pole, they're lined up, A and B, and this is 6:31 and 5 seconds. And they want to show you that this telephone pole is not this telephone pole. This telephone pole has a fire hydrant by it. That's how they're doing that. If this telephone pole was this telephone pole, it means that car A didn't move at all. But they're different telephone poles. This is the next one over. That's what they're showing you. So, the displacement of car A after 5 seconds. In 5 seconds, car A went from this pole to this pole. So it went 70 meters. Displacement of car B after 5 seconds. In 5 seconds, car B went from this pole, past this pole, to this pole. So it went 140 meters. The average velocity of car A during the 5 seconds would be 70 divided by 5, which I don't know off the top of my head. 70 divided by 5, 14 meters per second. The average velocity of car B went 140. 140 divided by 5, 40 divided by 5, 28 meters per second. Hey, that's kind of cool. You know, this number is twice as much as that number. Why do you think that is? Well, it's because this one went twice as far in the same time interval. So there's your answers. All right, to number 12. Let's take a look at 13. Take a look at 13. Thirteen says, Sally travels by car from one city to another. She drives for 30 minutes at 80 kilometers per hour, 12 minutes at 104 kilometers per hour, 45 minutes at 40 kilometers per hour. She spends 15 minutes eating lunch and buying gas. Determine the average speed for the trip. Determine the total distance traveled. I'm actually going to do these backwards. I'm going to figure out the total distance first. And you'll see why. If you did it the other way around, you'll still get the same answer. Okay, so she drove for 30 minutes at 80 kilometers per hour. Well, I know my equation that I've been using, average velocity is displacement over time. So I know 30 minutes, or sorry, 80 kilometers per hour We're looking for displacement. Her time is 30 minutes. I'm not going to use 30 minutes though, I'm going to use half an hour. 30 minutes is half of an hour. Because this thing is in kilometers per hour. We'll make this 0.5. 0.5 times 80, I get that she went 40 kilometers. Alright, so her first part of the drive, she went 40 kilometers. Then she goes at 105 kilometers per hour for 12 minutes. So let's see, 12 minutes. How much of an hour is that? In order to figure that out, I do 12 divided by 60. So there's 60 seconds in a minute. I get 0.2. 0.2. 0.2 times 105. So she went 21 kilometers for this part. Then, for 45 minutes, she was going 40 kilometers per hour. 40 kilometers per hour, we're looking for the displacement. 45 minutes is 0.75 hours. It's 3/4 of an hour. And, let's see, 0.75 times 40, she went 30. Right? So she went 30 kilometers. She went 40 kilometers, then 21 kilometers, then 30 kilometers. 40 plus 21 is 61, plus 30 is 91. So she went 91 kilometers total. That's my answer to B. Determine the total distance traveled, 91 kilometers. Determine the average speed for the trip. Well, you know, average speed is your displacement divided by time. If we want it for the whole trip, we'll put in our displacement for the whole trip, and we'll divide that by the time for the whole trip. The time was, let's see, half an hour. Let me add all these up. Well, I can do something fancy here, but I'm not going to. 0.5 plus 0.2 is 0.7. 0.7 plus 0.75, right? Plus the 15 minutes she was eating lunch, so plus 0.25. And her total time is 1.7 hours. Okay? The reason I counted the time she spent eating lunch is because that's still part of your trip. They want to know over the entire trip. So even if you're eating lunch, you still want to know over the whole trip. So 91 kilometers in 1.7 hours. Once again, I got that by just adding up all my times, including lunch. If I divide those two, 91 divided by 1.7, I get 54 kilometers per hour. 54 kilometers per hour. All right? All right. That's 13. Don't worry, they get tougher. Oh yeah, this one takes a while. Okay, so this is 14. This graph up here, which I'll scroll down to, shows the position of a runner at different times during a run. For the time interval between 0 and 10 minutes, what's the runner's displacement and average velocity? So here we go, this is 14. And we want to know from time 0 to 10 minutes. What's going on? They want both the displacement and the velocity. So from 0 to 10 minutes, her displacement is going to be how far she went. She started at 0, and she ended at, that looks like 22.5 to me. So she went from 0 to 2.5. Now you got to check this axis. This axis says position times 10 to the third. All right, 2.5 times 10 to the third will be 2500, and this is meters. So that's her delta x. That's how far she went. She went from 0 to there, to 2,500 meters. And they want to know her velocity. We can work out the velocity. Let's work it out in meters per minute. You know that the time from 0 to 10 minutes is 10 minutes. So consequently, the average velocity is going to be 250 meters per minute. Why per minute? Because my time's in minutes. I didn't change any of my times. So there's 0 to 10. I'm pretty sure the rest of these things just ask 10 to 20, 20 to 30, all that kind of stuff. Yeah, there we go. So from 10 minutes to, might as well stick with the same convention. I didn't like the first one. 10 minutes to 20 minutes. What happened? Runner's average velocity and their displacement. So from here to here, she went from 2.5 to 4.0. 4.0 minus 2.5 is 1.5. So her displacement was 1,500 meters. And her time was, she went from 10 to 20, so that took her 10 minutes. See how I'm taking the difference? Displacement's how far you are from where you start. So they want to know your displacement for this jump right here. Average velocity is displacement over time. It's going to be 150 meters per minute. Next one, let me guess. 20 to 30. Yep, 20 to 30. 20 to 30. What's going on? 20, she's at 4. 30, she's at 5. So she went 1, which times 10 to the third is 1,000. So she went 1,000 meters. It took her another 10 minutes. Your average velocity, 100 meters per minute. And then the last part asks, what's the runner's displacement for the total run? What's the runner's average velocity for the total run? So, total, she went from 0 to 5. Is that 5? I guess that's 5. She went from 0 to 5. So her total displacement is 5,000 meters. And her time went from 0 to 30. So she ran a 5K in like 30 minutes. Makes sense. It's pretty average. So yeah, her time is 30 minutes. So her average velocity would be, over the whole trip, 5,000 divided by 30, 500 divided by 3. 167 meters per minute. There you go. That's about my 5K time. Okay, so there's 14. Not difficult, just a lot of repeated stuff. All right, 15 I think is the last one. Yeah, last one in this section. 15 requires drawing some pictures. Get things straight in your head. So, let's do that. Here's a flagpole. These runners are running around a flagpole. There we go. Stars and bars. Beautiful flagpole. Okay, runner A is initially 6 kilometers to the west of the flagpole. 6 kilometers to the west, we have runner A. Getting ready to go. I'll label it A. Runner B is 5 kilometers to the east. 5 kilometers to the east. We've got runner B. And runner B is ready to go. All right. And these guys have velocities. So if we look back to runner A has a velocity of 9 kilometers per hour due east. So this guy's going that way, 9 kilometers per hour. And this guy is going this way at 8 kilometers per hour. What will be the distance of the two runners from the flagpole when their paths cross? It's not necessary to convert your answer from kilometers to meters for this problem. You may leave it in kilometers. No duh. Okay. I don't know why they didn't give you this clue on anything else. They give it to you here. And this is a harder problem. So here's what you got to think. You got to say, all right, I'm going to have to set up some sort of equation to tell me what's going on here. I know the total distance between these two guys is 11 kilometers. So I want to know when they're going to be done running 11 kilometers. That's the way I would look at it. And I would say, how far this guy ran, I can figure out by doing 9 kilometers per hour times the amount of hours he ran. That's from our velocity equation. Right? Your velocity equation, if you saw it for displacement, it's velocity times time. So his displacement is going to be his velocity times time, plus this guy's displacement is going to be his velocity times time. So when their two displacements added together equal 11, when they've closed all of this distance, that means that they've met. And now you got to solve this for t. All right? So I would get 17t equals 11. And if I solve that for t, if I do 11 over 17, I get 0.65. So these two guys meet after 0.65 hours. Now the question is, where do they meet? Well, you can figure that out by plugging this into either one of those displacement equations you just came up with. So you know that 9 times the time is where this guy's going to be. So if we do 9 times 0.65, we'll find out where he is when they intersect. 9 times 0.65, 5.85. So this guy's gotten 5.85 kilometers. He's almost gotten to the flagpole, right? So he's going to be, if you were to work that out relative to the flagpole, he's going to be 0.15 kilometers west of the flagpole. How do I know that? If this is 6 minus 5.85, which is the amount he's covered, leaves me with 0.15 kilometers. So he's 0.15 kilometers to the west of the flagpole. And that's where we think they intersect. So we could actually check our answer. We could figure out how far this guy's gone and see if that works out to 0.15 kilometers west of the flagpole as well. And if it does, we've solved it. So let's do that. 8 times 0.65. How far does this guy go in 0.65 hours? 8 times 0.65 is 5.2. Okay? So he has gone, according to our equation, to the flagpole and then 0.2 kilometers west of the flagpole. So if we work it out this way, we get 0.2 kilometers west of the flagpole. And the answer to the question, or the question you probably have is, well, this one's 0.15 and that one's 0.2. The difference told me, you told me they'd be the same. Why is that? Well, it's because we rounded this number. Right? 11 divided by 7, 17, is actually 0.647058824, so on and so forth. Okay? But I will tell you this, these are close enough. Right? You're off by 0.05 kilometers. In the grand scheme of things, if you want to work out, what that, you're off by 50 meters. Why is my computer telling me how to go home? Anyway, I need to, not time to go home yet, computer. So yeah, it's because of rounding is why it's off a little bit. All right? And you would still get credit for it on the test. All right, that is all the problems. This last one was probably the toughest.